Dear students, myself I am Srinivas Beti. I will be teaching the digital logic. This subject, digital logic, in the computer science, a GATE exam, you will be having the weightage generally between 5 to 8 marks. This subject is basically one of the basic subject and one of the core subject as far as the hardware is concerned. The knowledge of this subject, this digital logic subject, is useful to learn the CO subject, computer organization, advanced computer architecture subject, microprocessor or microcontrollers, if at all you are having in your academic syllabus. The basics of this digital logic is useful to learn the microcontrollers and microprocessor subject. And few of the concepts of this subject are useful even in the computer networks as well as in the operating system subject. So it is basically one of the basic subject, one of the core subject of hardware, in particular for computer science students, is one of the basic course. As far as learning of the hardware is concerned, it is useful for other extension if at all we are talking. It is useful even in the embedded systems. This subject possible, the subject we can split into basically 5 parts as far as the syllabus coverage is concerned. The subject we need to start with the basics. The basics of the subject is Boolean algebra. So under this Boolean algebra, we are looking basically first the various operators, Boolean operators. The Boolean operators, basic operators are concerned OR operator, AND operator, NOT operator, and also we need to speak the Boolean variables. We'll be looking properties on these Boolean operators, and we'll be looking the logic gates. We need to learn how to develop sum of product expression or the product of some expression using truth table or vice versa. A part of this, we'll be looking few of the operators with the name of derived operators. So under these derived operators, here we'll be learning Boolean variable operators. What we mentioned here, they are basically the basic operators. Here we'll be having the focus on OR operator, AND operator, and NOT operator. Whereas coming to these derived operators, we'll be looking here the NAND operator, NOR operator, exclusive OR operator, exclusive NOR operator, etc. And we'll be looking here few of the relations which are possible on XOR, XNOR operators, few of the relations which are possible on XOR, XNOR operators, and we'll be looking how to realize given Boolean function, how to realize the given Boolean function with minimum number of NAND gates as well as NOR gates. In particular, our focus is using minimum number of 2 input NAND gates and 2 input NOR gates. And a part of this, we'll be looking through the problems which are related with the properties, and of course, as I said, few of the relations which are possible on XOR and XNOR. Using these properties also we'll be working few of the problems. After this basic part of the subject, we'll be looking to the next topic is number system. So, under the heading of the number system, we need to learn more generic procedure how to convert a number which is having the base is R1 to another number which is the base of R2. So basically our work is conversion of the number from the radix of R1 to the radix of R2. So whenever we are learning this conversion, we are not limiting our learning just decimal to say nibble or decimal to octal or decimal to hexadecimal. We need to learn more generic procedure. Suppose I am having a number which is having a radix as say 9. How to convert this number as a radix of 3? Or for that matter, if I am having a number which is the radix of 10, how to read this number with the radix of 5? So like this more generic way, we need to look the procedure to convert the number which is with the radix of R1 to radix of R2. So after this primary work of this conversion, we'll be looking R minus 1's complement and R's complement. Later, signed binary number system. So these are the topics we'll be looking at the heading of the number system. Here we are not looking to the codes. I am not discussing at this point the BCD codes or gray codes or XS3 codes. Those things I am not discussing. In the due course, we'll be having coverage of those things. But here, under the heading of the number system, in our syllabus, when I am teaching this, under the heading of the number system, we'll be discussing these are the points. After this number system topic, we'll be moving back to the Boolean algebra work only. Here, we'll be learning Carnot maps. We'll be discussing here K-maps. Under the heading of these K-maps, basically our focus is few of the basic important terms which are related with the minimal expression. Basically, the work what we are going to do with the K-maps and the work what we will be having by using the Boolean algebra properties. By using the Boolean algebra properties, what is the work we will be having? It is coming to be more or less same. Basically, with this Boolean algebra properties or K-maps, our concern is for reading the minimal expressions, maybe reading the minimal SOP expressions or reading the minimal POS expressions. Or equivalently, we can speak for reading maybe simplified expressions. So when we are dealing the reading of the minimal expressions using Boolean algebra properties, we are having certain limitations. We are having certain limitations to read the minimal expressions or the simplified expressions using the Boolean algebra properties. These limitations are possible to overcome by using those K-maps. So in the due course, and with some examples in our syllabus, we are going to speak what are the limitations we are having to read the simplified expressions or to read the minimal expressions using properties. So after learning those things, basically we'll be looking to these K-maps. So K-maps is little systematic procedure for reading the minimal SOP or POS expressions. As I said already, while dealing with the simplification or the minimal expressions, we come across few of the terms. The terms what we come across very frequently is implicants, prime implicant, essential prime implicant, we come across very frequently this terminology while dealing with the minimal expressions. Even in any competitive examination, maybe GATE, or for that matter, any PSU, or maybe something defense lab exam or ISRO exam, we'll be having generally the questions related to this terminology. Most of the times, we'll be having questions related to this terminology. So I already said, with all this work, finally, our concern is for reading minimal SOP or minimal POS expressions. It is a concern. Until this, what are the discussion we'll be having in the class? The discussion is mostly related with the basic part of this subject, After this, the next topic we are starting, which is combinational circuits. The next topic will be starting, which is the combinational circuits. And the heading of this combinational circuits, basically we are trying to learn how to build the logic circuit, how to develop a digital circuit, or how to design a digital circuit. So whenever you're talking about how to design a logic circuit or how to develop a digital circuit, basically we are need to use hardware components. Those hardware components are nothing but the logic gates. So the logic gates, what we learned here in this basic part. So by using these logic gates, we are trying to implement the digital circuit, maybe implementing or maybe analysis or maybe designing of the digital circuit. That work we'll be learning in this under the heading of this combinational circuits. And various topics what we are having under the heading of the combinational circuits are, we'll be starting with the code converters. We'll be starting with this code converters. Again, here they are having different types of code converters. For example, BCD to say XS3 code converter, XS3 to BCD code converter, or binary to gray code converter, or gray to binary code converter. Like this, we can speak few different types of code converters. As I said, while discussing this number system, I said we are not discussing the codes. We are not discussing what is accessory code or what is a gray code. These things I said we are not discussing. While discussing the hardware of these circuits, we'll be discussing what is the means of accessory code, what is the means of gray code, what is the means of BCD code. These things we'll be discussing. We are avoiding the discussion of these codes under the heading of the number system. The reason is, if at all we are discussing here, while designing the hardwares for these code converters, again we are in need to know what is the means of these codes. If at all we are discussing here to develop the hardware or to design the hardwares, we are in need again the knowledge of these things. Maybe need to repeat a little extent. To avoid the repetition, I am not discussing those codes at this part. I will be discussing these codes under the heading of these code converters. After this topic, code converters, we will be looking arithmetic circuits. So under the heading of these arithmetic circuits, we are having various hardware blocks basically to perform arithmetic operations. The name itself, it is giving the means. The arithmetic circuits means the circuit supposed to perform the arithmetic operations. What are the different arithmetic operations we are having? They are the well known for us: addition, subtraction. These are the basic things what we need. So we are looking here addition and subtraction. Again, the addition and subtraction may be on single bit numbers, or the addition and subtraction may be on multi-bit numbers. So when we are having the addition and subtraction on multi-bit numbers, we suppose name as binary adder and binary subtractor. So binary number, if at all we are talking more generically, binary number consisting of more than one bits. So that whenever we are having the numbers with multiple bits, the addition and subtraction what we are performing they're supposed to be named as a binary addition. So based on this, the hardware what we are developing to perform such additions and subtractions, we must name as the binary adders, binary subtractors. As similar to that, the numbers are possible to represent with BCD codes. So we are having possibility to build the hardware circuits to perform addition on BCD numbers and to perform addition subtraction on the BCD numbers. So whenever we are building the hardware to perform addition and subtraction on BCD numbers, those circuits supposed to be named as BCD adders, BCD subtractors, etc. So all those things we'll be learning under the heading of these arithmetic circuits. A part of this, we will be looking the magnitude comparator, etc. So under the heading of these arithmetic circuits, as I said, we'll be discussing this of adder, of subtractor, binary adder, binary subtractor, BCD adder, BCD subtractor, magnitude comparator, etc. These things we'll be discussing under the heading of these arithmetic circuits as a subtopic of these combinational circuits. Later, the next topic we are having in these combinational circuits is multiplexers, demultiplexer, decoder, encoder, priority encoder, etc. These circuits will be discussing. Basically, we'll be learning how to build these circuits, multiplexers, demultiplexers, decoders, encoders, priority encoders, and also we need to know various applications of these circuits. So we need to speak the applications of these circuits or blocks. So until to this part is coming under the heading of the combinational circuits as far as our GATE syllabus is concerned. This is, I think, the fourth topic in our sequence. This is third, it is the fourth, I can speak. The next topic we are having is the last topic, that is sequential circuits. Under the heading of the sequential circuits, we need to start with the basics of binary latch, flip-flop, conversion, that say one flip-flop with the name of flip-flop 1 to another flip-flop with the name of flip-flop 2. So the sequential circuits, the basic part is this binary latch and these flip-flops. These are the basic part of the sequential circuits. So we need to start the sequential circuit topic with these basics. After learning these basics, in particular flip-flops. So while learning the flip-flops, we'll be looking the logic diagram of the flip-flop. We'll be looking the truth table, excitation table, characteristic equation of the flip-flop. After learning these basics on the flip-flops, we will be focusing in general how to convert a flip-flop with the name of flip-flop 1 to flip-flop 2. So whenever we are having this conversion work, we are not limiting our conversion work for only few of the standard things. We are not limiting. We are not bothering just for JK to D or JK to T. We are not limiting our discussion only these basics. So we need to know even the reverse. Whenever we are having a D flip-flop, how to convert a D flip-flop to JK, or whenever we are having a D flip-flop, how to convert the D flip-flop to T. Or more generically, we need to learn how to convert a flip-flop which is with the name of flip-flop 1 as a flip-flop 2. After learning this, after discussing this topic, we'll be looking to the circuits which are built by using these flip-flops. The circuits which are built by using these flip-flops are registers and counters. As far as our syllabus is concerned, we are having these registers and counters in our syllabus. So while looking to these circuits, we'll be looking in these circuits, we are having basically the usage of more than one flip-flops. The usage of the more than one flip-flops, we are having these registers and counters. Register is basically a storage device. Once it is a storage device, for any storage device, we will be having the operation. For writing the data facility, we need the operation. For reading the data from the device, we need the facility. So that when we are talking about the registers, we are looking to the various registers, the name of serial input, serial output register, serial input, parallel output register, parallel input, serial output register, serial input, parallel output register, and right shift, left shift, etc. Right shift, left shift, etc. These things we'll be learning on this register topic. And of course, while discussing the registers, we'll be talking few of the things as ring counter, twisted ring counter, etc. Later, we are moving to these counters. Counters we are having, one counter is asynchronous counter and other counter is synchronous counter. In the case of the asynchronous counter, a special case we are having as ripple counter. So these counters will be learning under the heading of these counters, how to realize or how to design a asynchronous counter or a ripple counter, or when we are naming a counter is a ripple counter, and when we are naming a asynchronous counter, every asynchronous counter may not be a ripple counter, but every ripple counter is an asynchronous counter. These differences, these things we need to learn. Later, we need to know the designing of these synchronous counters. So before moving to the synchronous counters, after completing the asynchronous counters, before moving to synchronous counter, we need to learn what is the basic difference between asynchronous counters and synchronous counters. Is there any limitation with the asynchronous counter? Is there any limitation with the ripple counter? These things we need to focus, we need to learn. So after learning these things, we are coming to design the synchronous counters. We'll be looking the analysis as well as the designing of these synchronous counters. When we are discussing these counters topic, whether it is asynchronous counter or ripple counter or synchronous counter, our concern is for designing, for implementation as well as for analysis. For both the things we need to learn. So on the whole, these are the various topics what we are having in our syllabus GATE. And for any public sector PSU exam is concerned, maybe ISRO or DRDO, even this type of exams, as far as the computer science students are concerned, they are having in this digital logic, maybe in few exams it may be named as a digital logic design, so subject name. Either it may be anything. The basic topics what we are having in this subject is these are the topics as far as the computer science students are concerned. And of course, it's a common subject among many engineering branches. For EC, for EE, for instrumentation, among many engineering branches, it's a common subject. For EC students, for EE students, there are few extra topics. Even for instrumentation students, there are few extra topics. But as far as the computer science students are concerned, these are the topics what we are having in our syllabus. GATE examination point of view, if at all you are looking, which are the topics which are little important? Of course, we can't make a distinguish, can't speak exactly. It is important, it's not important, that like that it's not possible to speak. But even though just I'm mentioning, as far as the GATE examination point of view, if at all you're looking, most of the times you'll be having questions from this basic part of the Boolean algebra. When I'm talking basic part of the Boolean algebra, means it is together this first and third topic what I listed, inclusive of the K-maps I'm talking. Most of the times you'll be having a guarantee question from this basic part. Even in the 2020 GATE exam, there was a question from this basic part. There was a question from this basic part. And you'll be having generally most of the times a question from this multiplexes, demultiplexes topic. In the 2020 GATE exam, there was a question, one question from multiplexer topic, one question from demultiplexer topic. And general sense, if at all you're looking, Boolean algebra and this K-map topic, from this 99% there will be a question. And number system, you'll be having a question most of the times, 80% you can speak. In 2020 GATE exam, there was no question from this number system. But in 2019, last year GATE exam, so we are discussing about, we are talking you as 2021 GATE students. So present 2020 recent exam, there was no question from this number system topic. But last year, 2019 GATE exam, there was a question from this number system topic. In fact, the question came with the weightage of 2 marks. And coming to these circuits, so most of the times you will be having a question from the multiplexer topic. If at all there is no question from the multiplexer topic, most of the times 99%, if the question is not from the multiplexer, so you will be having a question definitely from this counters part, or maybe sometimes from the register, from the sequence circuits. So general scenario, if you look, the basic part is very important. Later, from the combination circuits, I can speak the multiplexers. From the sequence circuits, I can say most of the times the question is from the counters. But the GATE exam is concerned, we are having total technical questions, 25 marks or 25 questions of 1 mark and 30 questions of 2 marks. So altogether we are having only 55 questions. These 55 questions are covering all the different subjects, and in every subject you are having number of different topics. So from which corner we are expressing question, it is very difficult to speak. From which corner you will be having a question, it is very difficult to speak. As a student, without taking any choice, you need to prepare. In fact, I'm talking in general. You need to prepare, you need to prepare without leaving any topic from any subject. To perform well in the GATE exam, it is very much required. It is very, very much required. So, we don't know from which corner you will be having questions. Sometimes the question may be little simple. Sometimes the question may be little twisted questions. So, based on this, don't assess any subject as easy or any subject as hard. This time, the questions from so-and-so X subject is easy, but you can't guarantee the same level of questions we'll be having next year. Or if at all, this year we are having little twisted question from one of the subject. Same twisted question you can't expect next year. It may be little easy. So, it is very dynamic and very vague. You can't make any graph easy or tough. You have to prepare a student each and every topic to perform well in the GATE exam. For this subject, the number of books are available in the market. The number of different books are available in the market. If at all you are asking me to suggest few good books, I don't want to list a couple of books. Just I want to name only very few books. One book, it is very good book as far as the GATE syllabus is concerned and GATE question paper pattern is concerned. Based on that, this book is one of the very good book. Modern Digital Electronics by R.P. Jain. It is one of the very good book. It will cover all the topics of GATE CSE syllabus. Most of you in your academic syllabus in the college, you might be used this book. Digital Logic Design by Maurice Mano. It is also a good book, but as for the GATE exam is concerned, if at all you are suggesting me to recommend, instead of this book, I prefer to recommend the first book. The first book, the syllabus content or the way of discussion, what you'll be looking is very relevant to the any objective type question paper. We'll be having couple of solved examples, many different solved examples, and very simple way we are having a discussion, very with a easy language we are having the topic discussion in this book. That is Modern Digital Electronics by R.P. Jain. Sometimes we are looking the questions, PSU exams, in the GATE exam, the questions which are available in this textbook are the direct questions in the GATE paper or in the ESC paper, for EC I am talking, or in the competitive examination or ISRO or DRDO, etc. This digital logic design, more theoretical description you will be looking. Related to this, the examples here not so good. Here the examples what you will be looking in every topic are very good examples. But of course, I am mentioning you can manage even with this book. If this book is with you, you can manage. But as I said already, again I am repeating, if at all you are suggesting me to recommend, I suggest you read the first book. Okay. Apart of this, the resources which are available from the MEDIC, those resources also you need to use a part of this. So, workbook, what is available from the MEDIC, and the theory book, what is available from the MEDIC. This theory book and workbook, a part of this, one important book is previous GATE solution book, solved solution book. The previous GATE solution solved book is very important book for you. So, from the class notes, while making proper notes while teaching, from the class notes and using workbook and solving yourself, possible extent the workbook questions. While solving the workbook questions, and if you want some extra questions, of course you can refer to the theory book. Theory book also you are having some extra questions. And while solving the previous GATE previous GATE book questions, of course solutions are available in the MEDIC, from the MEDIC what you are getting. So while solving these questions, you will be having complete command on this subject. But while listening these notes, or while listening these classes, make proper notes. That is very important. The workbook questions, what order you will be looking in the workbook? That order is almost the same order what I am going to teach in the class. What I am going to teach in the class. Thus, within the sub-topic, if at all we are talking the combination circuit, what order I mentioned, the same order you are having questions in the workbook. And if at all we are talking about the sequence circuits, what order I mentioned in the sequence circuit subtopics, the same order you will be finding there. And syllabus coverage will be having the class 99% only with this order. Based on the time availability, sometimes a small change may be there, but most of the times this is the order we'll be following in the syllabus coverage. So we'll be starting with the Boolean algebra, later we'll be shifting to the number system, later K-maps. After completing the basic part, we are switching to the digital circuits as combinational circuits and sequence circuits. This order we prefer to follow. So in the beginning of the class, I said the weightage of this subject will be vary between 5 to 8 marks. If you look 2020 GATE exam, in the 2020 GATE exam, the weightage came from the subject of 4 marks. In the 2019 last year GATE paper, the questions came from this subject with a weightage of 7 marks. And 2018, it came with a weightage of the 6 marks. If you look to the last 5-6 years question papers, and if you look to the weightage, generally the weightage will vary somewhere between 4 to 8 marks. So on average, we can speak 5 marks we'll be having as a guarantee question. And of course, once we are talking weightage of the 5 marks means it may be a question 2 marks questions 2, 1 mark question 1, or it may be the case a 1 mark question 3, 2 mark question 1, etc. So it is a weightage what we are having. We are having the usage, the importance of this subject even in the interviews. So sorry, the defense lab interviews or ISRO interviews, generally you will be having questions, little bit difficult questions from this subject, because most of the seniors, most of the those who are examining you, those who are taking interview to you, most of the people are the senior scientists or senior people. Those senior scientists, senior people are mostly they are with the background of the electronics. Because of this, as a computer science students, you may be attending interview, but you will be having little bit difficult questions from this digital logic subject. Okay, so hope you noted what I mentioned on the board. We'll start after this our subject. If you look to the development of this subject is basically developed using Boolean algebra. If you look, the difference between the algebra what we learn in the schooling and this Boolean algebra. The algebra what we learn in the schooling is the conventional algebra. The conventional algebra is based on the number system which is having the base as 10. Whereas this Boolean algebra is based on the number system which is having the radix, that is the base as 2. So the conventional algebra is based on the decimal number system, whereas the Boolean algebra is based on the binary number system. In this conventional algebra, we are dealing with the equations and expressions. In these equations and expressions, basically we are relating the variables by using few operators. As similar to this conventional algebra, even in the Boolean algebra also, we are dealing with the equations and expressions. So here also, in these equations and expressions, we need to relate the variables by using few operators. While dealing with this Boolean algebra also, as I said, we are dealing with the equations and expressions. In these equations and expressions here also, we are basically relating the variables by using few operators. As similar to this conventional algebra, here also the variables we are representing may be with this uppercase letters or maybe with this lowercase letters. And to relate these variables, we are having here the operators or operator and operator and not operator. These are the basic operators. By using these operators, it is possible to relate the variables so that it is possible to read the equations and expressions on these variables. Out of these three basic operators, the first two operators are binary operators, whereas this not is unary operator. Once we are talking a operator is a binary operator, it will associate with a minimum 2 operands, whereas unary operator is associate with only 1 operand. So that when we are talking about this OR operator or AND operator, we need to deal with a minimum 2 operands, whereas this NOT operator is unary operator. We need to start this subject with these operators. This R operator symbolically represented by using any one of this symbol. If A and B are the binary variables or Boolean variables, you can name these Boolean variables as the binary variables also, because as and when we are talking, the number system is binary number system. The discretes we are having only 0 and 1. Based on this, the Boolean variables we can name even as the binary variables. So whenever we are looking, A and B are two Boolean variables or binary variables. While having OR operation among these operands, by using any one of this symbol, OR operation among these operands we can write with any one of these symbol by using any one of this symbol. The result of this operation also let us name with a Boolean variable as a y. In general, it may be on any number of operands. Whenever we are having a operator as a binary operator, to look to the result of the binary operator, we prefer to look to the result maybe with an example of the 2 variable and 3 variable. While knowing the result of the operator on 2 variables and on 3 variables, it is possible in general to speak the result of the operation on any number of operands. Suppose if at all we are looking to the result of our operation on 2 variables, say on A and B, the possible values if we list on these variables, the possible values may be 0, 0 or 0, 1 or 1, 0 or 1, 1. Similarly, if at all we want to look to the result of the operation on 3 operands or on 3 variables, the possible values on these 3 variables are coming to be any one of this combination. While having OR operation on these 2 variables, we are having the result as for first row it is 0, for the remaining rows it is 1. Similarly, while having OR operation on these 3 Boolean variables, the result other than the first row, for the remaining rows, the result is 1. So while looking to these tables, it is possible to make a statement on this OR operation as the result of OR operation is 0 if and only all the variables are 0. It is possible to speak a statement, you can note it, the result of OR operation is 0 if and only all the variables are 0. So we are looking whether it's a 2 variable or 3 variable or in general on any number of variables if you speak, the result of the OR operation will be 0 only for the first row. That is the only row we are reading with all the values, all the variables will be having the values as 0. So that we are speaking the result of OR operation is 0 if and only all the variables are 0. Or equivalently we can talk the result of OR operation is 1 if at least one of the variable is 1. Other than the first row, you can see either maybe 2 variable or 3 variable. Other than the first row, for the remaining rows, guarantee at least one variable is 1. So that the result of OR operation is 1 if at least one of the variable is 1. To perform all these logical operations, we are having hardware devices. These hardware devices are named as logic gates. To To perform all these logical operations, we are having hardware devices. These hardware devices are named as logic gates. To perform our operation, we are having the hardware device with the name of OR gate. This OR gate symbolically represented like this. It may be having any number of inputs. It may be having any number of inputs. The number of inputs to a logic gate is called fan-in of the logic gate. Say for example, we are having a OR gate with 4 inputs. Then the fan-in of that OR gate is 4. Or equivalently we can speak, the fan-in of a OR gate, the fan-in of a given OR gate is 3. Then default it is indication that particular OR gate is having 3 inputs. It is a means of the word fan-in. Fan-in is the word which is referring to the number of inputs of a logic gate. These logic gates are basically built by using electronic components, by using basically electronic devices such as semiconductor PN junction diodes, bipolar junction transistors, or field effect transistors. Basically, the logic gates are implemented by using semiconductor devices such as diodes and transistors. The transistors may be BJT or maybe field effect transistor. Say for example, as a matter of interest, if we look for a 2-input OR gate, what is the inside hardware for a 2-input OR gate? What is the inside hardware or inside circuit? Suppose this 2-input OR gate is implemented by using PN junction diodes. Having 2 inputs, inside circuit will be having 2 PN junction diodes. It is using 2 PN junction diodes. One diode, say D1, anode is named as a input, other diode D2, this diode anode terminal, input terminal, let us name as a B, and output of this circuit is Y. And when you speak, this OR gate is implemented by using these diodes. Inside circuit we are having, basically it is a circuit we are having inside. From the knowledge of the diode operation, it is possible to look to the operation of this circuit. The logic levels, logic 1, logic 0, what we are talking, these logic levels basically are the voltage levels as far as the electronic circuit is concerned. As far as the electronic circuit is concerned, what we are talking, this logic 0 or logic 1 are the voltage levels. So 2 different voltage levels are used. Suppose logic 1 we are having the usage of say plus 5 volts, logic 0 say 0 volt. If you want to see the voltage drop across this resistor, then there must be current through this resistor. If at all we are having some current that is non-zero, some current as and when it is flowing through this resistor, then there will be voltage drop across this resistor. That voltage drop will be reading as the logic 1 level, logic 1 voltage. If at all the current through this resistor is 0, if the current through this resistor is 0, then the drop across the resistor is 0. Because of this, we are looking to the output is a logic 0. So, if at all we are looking some current through the resistor, then only it is a logic 1. If there is no current through the resistor, the logic level is a logic 0. If you want to see the current through this resistor, then definitely we need at least one of these diode must be on. The on state, if at all you are remembering, you might be learned few of the basics of this junction diodes in your 12th class or in your engineering first year. If at all you are remembering well, okay. Otherwise, also just a brief review I'm mentioning. On state is named on the PN junction diode as a forward bias. Off state is named on the PN junction diode is reverse bias. So whenever the diode is on, that is in forward bias, at least when the diode is a forward bias, there is a finite amount of current through the diode. Whenever there is a current through the diode, that current has to flow through the resistor R. Hence, we are having the output is logic 1. If at all the diode is in the off state, if the diode is in the off state, and of course, there is no current, off means diode is open, no current means there is no current through the resistor, that is giving the output is a logic 0. So, having this basic knowledge on the PN junction diode, if you look to the operation of this circuit, as and when at least one of the input is logic 1, as and when at least one of the input is a logic 1 means one of the input is plus 5 volts. So, one of the input is a logic 1 or one of the input is a plus 5, basically it is referring to this last 3 rows of this table. As and when at least one of the input is logic 1, we are looking one of the diode is on. Because of this, we are having here non-zero current. When we are having a non-zero current, we are having output is logic 1. So it is a one what we mentioned in this table for the last 3 rows. Whenever at least one of the input is 1, we are having the output is a logic 1. As and when A and B both are logic 0, whenever both are logic 0 is referring to the first row of this table. Whenever both are logic 0, we are having diode D1, diode D2 both are in the off state. When both are in the off state, the current through this resistor is 0. When the current through the resistor is 0, output is 0. So that is the one what we mentioned in the table. So if you look like this, the operation of the circuit is following the operation of this 2-input OR gate. Hence, we mentioned if at all this OR gate is implemented by using these PN junction diodes, it is the inside circuit what we are having. Like this, we are having implementation possible even maybe using the bipolar junction transistors or maybe using field effect transistors. But as far as our digital logic subject is concerned, we are not in botheration to know inside hardware of these logic gates. It is not our concern to know the inside circuitry of these logic gates. Without any knowledge of this electronics, without any knowledge of this inside circuitry of these logic gates, maybe of any gate, without the knowledge of any logic gate inside circuit, it is possible to learn this subject. So that as far as the subject learning is concerned, we must treat the logic gates itself as the basic devices or as the basic components of the subject. The subject learning is concerned, we need to consider only these logic gates itself or the logic gates itself we need to consider as the basic devices or the basic components of this subject. And as a matter of interest, if you look, if you want to have a 3-input OR gate, if you want to have the 3-input OR gate, based on this you can speak easily. Having 2-input OR gate, we are having inside circuit 2 diodes. If at all we want to have the OR gate with 3 inputs, then definitely one more diode will come in parallel with this D1, D2. If we want 4 input, then 2 more diodes will come in parallel. So based on this, our understanding is as and when the number of inputs are increasing, the cost of the logic gate is increasing. As and when the number of inputs are increasing means we are adding additional PN junction diodes. So whenever we are adding this PN junction diode, default it is indication cost point of view, the cost is increasing. Hence, when we can speak now, fan in is increasing means default the cost of the logic gate will increase. Hence, whenever we are talking the estimation of the cost of any digital system, estimation of the cost of any digital circuit, a part of the number of logic gates, the fan-in also one parameter to estimate the cost of the logic circuit. The fan-in is less means the cost is less. If the fan-in is more means the cost will be more. Here in this table, we are having two variables. Because the two variables, total number of rows in the table, we are having 4. Our total number of combinations in the table, we are reading as 4. Whereas this table is developed on 3 billion variables. Because of 3 billion variables, total number of combinations or total number of rows we are having in this table are 8. These tables are named as truth tables. These tables are named as truth tables. So what we are looking here is, we are basically listing all possible combinations of the variables along with the result. All possible combinations of the variables along with the result we are listing. So if we want to speak the definition of the truth table, it is possible to speak as truth table is the one which is consisting of all possible combinations of the variables along with the result. So you want to note, I will repeat, truth table is the one consisting of all possible combinations of the variables along with the result. Truth table is the one consisting of all possible combinations of the variables along with the result. While looking to these two examples, more generic case we can speak now. If at all we are developing a truth table on n Boolean variables, we'll be having total 2 to the power of n number of rows or 2 to the power of n number of combinations in the truth table. And generally, these combinations we are listing in the decimal increasing order, 0, 1, 2 and so on to the power of n minus 1. Generally, we prefer to list these binary combinations in this decimal increasing order. You can see even here also that order we followed. For each one of these binary combination, if you look to the equivalent decimal value, this is 0, this is 1, this is 2, this is 3. So having two variables, 2 to the power of 2 is 4, 4 minus 1, it is a 3. So that last row combination, decimal equivalent value is 3. Similarly, on 3 variable case, we are looking 0, 1, 2, 3, 4, 5, 6 and 7. So based on this, we mentioned whenever we are developing a truth table on n Boolean variables, we will be having total 2 to the power of n number of rows, and we prefer to list the combinations in this decimal increasing order 0, 1, 2 and so on to the power of n minus of 1. Let's come to the next operator, that is AND operator. It is also binary operator. Symbolically, we are representing this operator maybe by using any one of this symbol. If A and B are Boolean variables, AND operation we can write among these operands by using any one of this symbol. As a binary operator, in general, it may be on any number of operands. Here also let us try to look the result of this AND operation on 2 variables and on 3 variables. On 2 variables, we are having the result as 0, 0, 0, 1. So except the last row, for the remaining rows, the result is 0. Similarly, in 3 variables also, we are looking to the last row result is 1. For the remaining rows, the result is 0. So while looking to these truth tables, it is possible to speak a statement on the AND operation as the result of AND operation is 0 if at least one of the variable is 0. I am repeating, the result of AND operation is 0 if at least one of the variable is 0. Whether we are looking to 3 variable or 2 variable case, we are looking other than the last row, other than this last row, guarantee at least one of the variable is 0. So we mentioned because of this, the result of AND operation is 0 if at least one of the variable is 0. Or equivalently, we can talk the result of AND operation is 1 if and only all the variables are 1. If and only all the variables are 1. All the variables will be 1 only for the last row, whether it's a case of 2 variable or 3 variable, or even if you go for further 4 or 5 variable case also, only for the last row we are having all the variables are 1. So the result of AND operation is 1 if and only all the variables are 1. To perform this AND operation, the logic device is AND gate. Symbolically, this AND gate is represented with this symbol. It's symbolic representation for this AND gate. On these logic gates, a part of developing these truth tables, we need to look little more information on these logic gates. The information what we want on these logic gates is, if one of the input of the logic gate is 0, what is the output of the logic gate? If one of the input of the logic gate is 1, what is the output of the logic gate? If input A and B, we are limiting our discussion for 2 input case, connected to the same variable, say X, what is the output of the logic gate? If input A and B are not connected to the same Boolean variable, then what is the output of the logic gate? So this type of information we need in general on every logic gate whenever the logic gate is with more than 1 inputs. Whenever the logic gate is having a fan in more than 1, on all such logic gates, it is preferable to read this type of information. If you take the question why we are in need of this type of information on the logic gates, with a simple example, we can understand why it is preferable to know. Very regularly, very frequently, we'll be having questions. Something like this. Some logic circuit will be given using different logic gates. Some logic circuit will be given by using different logic gates. So some logic circuit is given here, of course, using few AND gate, 1 AND gate, 3 OR gates. And based on this, we are looking the circuit operation is depending upon the 4 variables. The variables on which it is depending is A, B, C and D. On these 4 variables, it depends. And you will be having a question generally as, and even this type of question, the logic circuit based question was there in the 2020 gate exam, recent gate exam. There was a question related to this logic circuit. So you'll be having a question as something like this. What is the output of the given logic circuit if at all the B input is 1 and D input is 0? We'll be having a question as, for the given logic circuit, what is the output F if the variable B is 1 and the variable D is 0? So we are looking here, the circuit depend on these 4 variables. Out of these 4 variables, we are looking A and C variable values are not mentioned in the problem description. The value of A and C variable is not mentioned in the problem description. Only the B variable and D variable values given in the problem description. While looking to circuit, while knowing the truth tables of these logic gates with the known values or with the given values, it is possible to speak the circuit output is 1. To read the circuit output is 1, we are not bothering what is the output of this gate 1, we are not bothering. What is the output of this gate 2, we are not bothering. While looking to this gate 3, one of the input is a B. B is mentioned as a 1 from the knowledge of the truth table. As and when one of the input of the OR gate is 1, the OR gate output is 1. So based on the knowledge of this OR gate, we are able to speak the gate 3 output is 1. And we are looking here, this gate 4 also OR gate, the gate 4 also again we are looking one of the input is 1. Hence, we are reading the circuit output is 1. So, without bothering or without wasting time to know what is the gate 1 output, gate 2 output, just looking at gate 3, one of the input B as a 1, we are able to speak the answer without doing any much work. The circuit output is 1. Of course, I quoted here very simple example, the discussion what we did till now based on the gates. But this type of circuit you may be having, maybe using some other gates like NAND gate, NOR gate or XOR or XNOR gates also. It may be of anything. While knowing the truth table knowledge on the respective logic gates, sometimes it is possible for us to speak the result of the circuit with less paperwork. So to speak these type of answers with less time, of course in the competitive examination, as you know, for any competitive examination, we must give the right answers. A part of the right answer in the competitive examination, one other important thing is how much time you are spending to answer the question. That is also important. For university exam, the time constraint may not be so serious, but definitely for competitive examination, a part of the giving the right answer, how much time you are spending to answer to the question, that is also equally matters. If at all we are having a question, the weightage the 1 mark, for 1 mark question, proportional time we must spend most of the competitive examination. For 1 mark question, the proportional time is 1 minute. For 1 mark question, if at all we are spending say 2 minutes, 3 minutes, definitely it is not worthy. At all 1 mark question, at the maximum we are spending 1 minute, that is beneficial. So that how much time we are spending, that is also matters. As an example, what I quoted is simple example. To analyze the circuit, if at all we are having a knowledge, something like this, if one of the input of the OR gate is 1, the result of the OR gate is 1, that knowledge if at all we know, without much time spending, we are able to speak the answer to this circuit is 1. Hence, in general, as I said, I already mentioned, whenever we are learning these logic gates, the gate is having fan in as more than 1. On all such gates, we will be trying to look to the information of like this. So if you look here, this information on a OR gate, based on the description we are looking, based on the description what I mentioned for last 2 cases, we are looking, the discussion we are limiting on a 2 input case. Of course, the knowledge what we are having on a 2 input logic gate, this knowledge possible for us to extend even any other gate with more than 2 inputs. If you look here, as and when one of the input of the logic gate is 0, while looking at the truth table of the OR gate, in specific, while looking at the first 2 rows of the truth table, in the first 2 rows we are looking A is 0. While looking at the first 2 rows of the truth table, we are speaking if B is 0, output of the OR gate is 0. If B is 1, output of the OR gate is 1. Hence, we are speaking it is a B. Hence, we are writing here whenever one of the input of the OR gate is 0, the output is same as the other input B. Whenever one of the input is 1, whenever one of the input is 1 is referring to the last 2 rows. First 2 rows are one of the input is 0. Next 2 rows we are looking, it is referring to the last 2 rows. Whenever one of the input is 1, we are looking, this B may be of anything. Irrespective of the B, we are reading output is 1. Hence, as and when one of the input of the logic gate is 1, we are reading output is 1. Without bothering what is the other input, we are speaking output is 1. Similarly, whenever input A and B both are connected to same Boolean variable, say X. Whenever both the variables are connected to same variable, X means it is referring to either maybe to the first row or maybe to last row. In the first row, it's the case X is 0. The last row, it's the case X is 1. So we are looking here, if X is 0, output is 0. If X is 1, output is 1. Hence, whenever both the variables are connected to the same variable, output is same as the input, that is X. Whenever both the inputs are not connected to the same Boolean variable, when both the variables are not connected to the same Boolean variable, based on the description itself, we are understanding one of the variable guarantee as a 1. If A is 0, based on this condition, B must be 1. Or if B is 0, based on this condition, A must be 1. So whenever we are looking this condition is true, guarantee one of the input will be 1 for OR gate. Hence, output is 1. Or alternatively, we can read even from the truth table while looking to the middle two rows. While looking to the middle two rows, we can speak whenever A and B are not same, output is 1. So this type of work, as I said, we need to work on every logic gate whenever the gate is having the fan in more than 1. You can try with this knowledge on the AND also. So to try on the AND, of course, there is a truth table we can use, or without referring to truth table with the definition also we can speak. Either way, we can try. So if you try, then definitely the results will be like this. Whenever one of the input is 0, output will be 0. Whenever input is 1, for 2 input case, output is coming to be same as other variable. As I said, you can see the truth table, from that also you can speak. Whenever one of the input is 0, first 2 rows, we are having here B may be of any value, output is 0. Whenever one of the input is 1, if B is 0, output is 0, B 1, output is 1. So we are speaking it is same as the other input, that is B. Similarly, if you come to next case, whenever both the variables are connected to same Boolean variable, say X, X may be 0, X may be 1. If at all X is 0, it is referring to the first row. If X is 1, it is referring to the last row. So based on these results, we are speaking whenever both the variables are connected to X, output will be same as the input, that is X. When both the variables are not connected to the same Boolean variable, and both the variables are not connected to the same Boolean variable means we are looking to the middle two rows. From the middle two rows, you can speak from this table, it is 0, or alternatively looking to the truth table, looking to the definition of the AND also you can speak. Whenever both are not same means one of the input to the AND gate guarantee is 0. Once one of the input to the AND gate is 0, the AND gate result will be 0. So that output is 0. So this type of work or this type of listing possible for us to give on every logic gate whenever the logic gate is having more than one inputs. A part of this, we need to look enable and disable inputs. A part of this, we need to look this enable and disable inputs. Again, this enable and disable inputs, we need to identify on every gate whenever the gate is having more than one inputs. If you look at the meaning of enable or the meaning of the disable input, enable input will make the device is to be active. The disable input will make the device is to be inactive. The meaning of the active means the response of the circuit, the response of the device is depending upon the remaining inputs. The meaning of the inactive means the response of the device or the response of the circuit is not depending upon the remaining inputs. So enable input will make the device is to be active. Suppose I am having a AND gate with 3 inputs. We need to identify enable input. That enable input, if we identify well, then the response, suppose we identified enable input is 1, then the response is depending upon the other 2 inputs. If at all B is 0, then we are looking, the response of device is independent of other 2 inputs. So based on this, I said the enable input will make the device is to be active. The disable input will make the device is to be inactive. So it is the means of the words enable and disable. If you are remembering well, I can quote a little higher level example. In the case of the sequence circuit, we are having the usage of the clock signal. Until we are not providing a clock signal, the circuit state, normal situation I am talking, will be inactive state. The circuit may be having any number of inputs. Until we are not providing the clock input is 1, the circuit is not getting the normal operation. It means if we are not providing clock, that is giving the device operation, circuit operation, inoperative state or inactive state. As and when we are providing the clock signal, the circuit operation will be depending upon the remaining inputs. So circuit operation is depending upon the remaining inputs, meaning is circuit is getting the normal operation. It is in the active state. So it is the means of the word enable and disable. Enable will make the device is to be active. Better to note, enable will make the device is to be active. The disable input will make the device is to be inactive. The disable input will make the device is to be inactive. Enable input will make the device is to be active. So if you look here for OR gate, enable input is 0. Disable input is 1. We can verify. Suppose I am having this OR gate 3 inputs. So operation is A or B or C. When B is 1, we are reading output is 1. From the definition of the OR gate or looking to the truth table, you can speak it is 1. It means output is independent of the variable A and C. Output is depending upon only on this particular variable B. Whenever output is independent of other variables, it is an inactive state, inoperative state. Hence, we are speaking the disable input of the OR gate is 1. Similarly, if B is 0, from the truth table, you can verify the operation is depending upon other 2 variables. Other 2 variables are A and C. The operation is depending upon A and C. Means, whenever B is 0, the other variables are giving influence to read the output. Our output is depending upon other 2 variables. Based on this, such input on this OR gate must be named as enable input. It is the one what we said alternatively. Enable input will make the device is to be active. So enable input, this 0 for OR gate, it is making the device is to be active, means other variables are allowed to pass. So in the active state, other variables are allowed to pass. In the inactive state, other variables are not allowed to pass. So such words we are having the usage with this enable and disable inputs. As similar to the OR, if you identify the enable and disable inputs, the enable input for AND gate is 1. Disable input will be 0. Same way as what we said on the OR gate, you can look here also. If B is 0, A and C may be of anything, output is 0. B is 0, output is 0. Other variables are not allowed to pass. Such state of the device we named as a disabled state. Such state of the device we named as a disabled state or inactive state. And whenever this B is 1, we are looking to the output which is depending upon other two variables on A and C. It depends. From the truth table you can verify. It is depending upon A and C. So this 1 is making the device is to be active. Hence the enable input of this AND gate is 1. So disable input is 0, enable input is 1. In general, as I said, we need to work this enable and disable inputs also on every logic gate whenever the logic gate is with more than one inputs. In our list, the next operator we said not operator. This not operator symbolically we are representing maybe with this symbol or maybe with this symbol. So we mentioned already it is a unary operator. Hence it is associated with only one operand. If the operand is A, the not operation on this variable we can write by using any one of this symbol. As a unary operator, because of one operand, the truth table we are looking the possible value on the variable may be 0, may be 1. While taking the variable as A may be 0 or A may be 1. We are looking here the result as Y is not equal to A. When A is 0, not equal to 0 stands for 1. When A is 1, not equal to 1 stands for 0. So it is a truth table of the NOT gate. Sorry, it's the truth table of the NOT operation. The device which is performing this NOT operation, we must name as NOT gate. The NOT gate symbolically represented with this symbol. Symbolically, it is represented with this symbol. This also named as inverter. This NOT gate also named as inverter. The word inverter with well meaning we can understand looking at the truth table. Basically, we are looking interchanging of the Boolean constant between input and output. That is the reason why we suppose name it is a inverter. While learning any mathematical subject, few of the standard relations what we need to use very frequently. Such relations we used to name as properties. So in any mathematical subject we are in need of properties to cut down the paperwork, to cut down the number of steps. So it's a normal situation, normal scenario. Whenever we are learning any mathematics subject, few of the standard relations we used to list as properties. As similar to any other mathematical subject, here also possible to list few of the relations on these operators. Few of the relations is possible to list on these operators. So those relations we are listing here under the heading of Boolean algebra properties. These relations we are listing under the heading of this Boolean algebra properties. A or with A any number of times it is A. Similarly, A and with A any number of times it is A. Of course, We can understand how we are writing this while looking to the truth tables or while looking to the listing what we are having here. A or with A, if at all A is 0, so it is coming to be 0 or with 0. Of course, any number of times, the result is 0. If A is 1, 1 or with 1, any number of times, it is 1. Similarly, the second one what we mentioned, A and with A, any number of times, it is A. So, if at all A is 1, 1 and with 1, any number of times, 1 and with 1, any number of times, it is 1. Or if at all A is 0, 0 and with 0, any number of times, it is 0. So, you can see maybe from the truth table or maybe from these results we can speak. So, what we mentioned earlier, that only of course I am listing here systematically as one of the property I mentioned. Similarly, we are going to look few more relations, few more properties. A or with 0 is A. A and with 1 is A. A or with Boolean constant 1 is 1. A and with Boolean constant 0 is 0. A and with its complement is 0. A or with its complement is 1. Of course, these relations also we are looking from the work what we are having there. If you see here, the last one is nothing but whenever A and B are not connected to same Boolean variable, whenever A and B are not connected to same Boolean variable is the last one. So, based on this, you are looking A and with A complement, A and with A complement is 0. Similarly, A or with A complement is 1. And middle twos, if at all you are looking, they are nothing but referring to whenever A is 0 or whenever A is 1, what is the output of OR gate or what is the output of AND gates respectively. So, what we listed there, in fact, those things only I mentioned here. And you can see here, but the listing we are looking, in all this listing, we are looking as a pair. The listing we are reading as the pair. If we observe a little closely, within the pair we are looking, there is a specific relation. Within the pair we are reading a specific relation. The specific relation, the observation what we are having is, in the equation X, if at all we are looking to the OR operation, while coming to Y, it is changed to AND operation. In the equation X, the operator is OR operator, then while coming to Y, this operator is changed to AND operator. Similarly, if you observe there, in the equation X, if it is AND operator, while coming to Y, that changed to OR operator. So basically what we are looking is, we are having interchanging of this operators. We are having interchanging of these binary operators OR and AND. And also we are observing, we are having interchanging of the Boolean constant 1 and 0. We are looking to the interchanging of the Boolean constant 1 and 0. In general, on any two expressions or equations, if at all we are having such relation, we are having any pair with such relation, such pair we are naming as dual pair. Such pair we are naming as dual pair. And this property we are naming as principle of duality. This property is named as principle of duality. So, in the principle of the duality, what we are looking is, we are having interchanging of OR and operators and interchanging of the Boolean constant 1 and 0. It is one of the important property. Generally, we will be having the questions based on this property. We will be having questions based on this property. There was a question in the 2018 paper based on this. 2016 also there was a question. So, very regular, very common questions we will be having based on this property. Let us try a simple question. So note down, find the dual of the given Boolean expression. Find the dual of the given Boolean expression. Find the dual of this given Boolean expression. It is a question. So you can try this, but while trying, be careful. Don't get confused between the dual operation, the De Morgan's operation. Both are different. Dual and De Morgan's operation both are not same, both are different. Anyway, the due course will be looking, after little time, we'll be looking what is the De Morgan's property. But be clear, both are not same. When we are having a Boolean expression, something like this, more than one parenthesis, if at all we are having the Boolean expression, the dual operation we need to apply first to the innermost parenthesis. The given expression is having more than one parenthesis. The dual operation we need to apply to the innermost parenthesis. This expression is concerned, this is the innermost parenthesis. So that we need to start our work from this innermost parenthesis. This OR operation must be changed to AND operation. Among this D and E complement, AND operation becomes OR operation. This OR operation becomes, this AND operation becomes OR operation. Finally, this AND operation becomes OR operation. This AND operation becomes OR operation. So that for the given Boolean expression, it is the dual result. It is the dual result. So you can see here, we are starting from innermost. It is the innermost. So this OR operation becomes AND. Among D and E complement, AND operation becomes OR. This AND becomes OR. Finally, this AND becomes OR. Hence, this is the dual of the given Boolean expression. Try to speak what the means of the word variable X. Similarly, what is the meaning of the word literal X? These are the two words, common words, which we come across very frequently while dealing with the Boolean equations and expressions. Or in general, while working with the Boolean algebra, we come across very frequently these words. The words are variable X and literal X. You can guess what the means of these words. You speak the word variable, truly speaking, strictly speaking, the word variable is referring to only uncomplimentary form of the variable. It is referring to only uncomplimentary form of the variable. If we want to read the complementary form of the variable, then definitely we are in need of a NOT operation. We are in need of a NOT gate. Hence, truly speaking, the word variable is referring to only uncomplimentary form of the variable. Whereas the word literal is referring either maybe to uncomplimentary or complementary form of the variable. It is referring to the word either maybe uncomplimentary or complementary form of the variable. It's the means of the words variable and literal. The word variable is referring, strictly speaking, to only uncomplimentary form of the variable. Whereas the word literal is referring to either maybe uncomplimentary or complementary form of the variable. Using this terminology, we can talk about this dual operation. In the dual operation, the literals are not affecting. In the dual operation, the literals are not affecting. It is observation what we are having from the example, what we are looking on the board or what you tried yourself. Here we are looking, the B variable is the complement after dual operation is coming with the same complement. C variable was without complement in the given expression. After dual operation, C is coming without complement and so on. Hence, we are having a conclusion. The dual operation, there is no effect on the literal. So, literal is not changing. Literal is ineffective. Ineffective with the dual operation. It is very important to note. So, with the dual operation, effective changes is on operators, on binary operators or and on the Boolean constant 1 and 0. There is no effect of the dual operation on the literal. So, literal is ineffective with the dual operation. It is ineffective with the dual operation. Okay. Let us come to further listing of these properties. If a variable A is complemented twice, it is same variable A. Can speak easily this. Suppose the Boolean variable A is 0. While taking complement on this variable, it is 1. While taking one more complement, it becomes 0. We started with 0, we are reaching to 0. If we start with 1, we will be reaching to 1. So that we are speaking with the variable A is complemented twice, it is the same variable A. A or with BC is equal to A or B and with A or C. It is one of the important property. Very frequently we will be having questions based on this property. You can guess the name of this property. This type of properties will be having in normal algebra also. Many places you come across this type of relations. So you can guess the name easily. Hopefully you might be guessed. The name of this property is distributivity. The name of this property is distributivity. What are the relations we listed till now? That is until to 4. We are having proof for all these relations from the work what we had from the truth tables. From the work what we had with the truth tables, we are having the proofs for all these relations. You can check easily. So whenever one of the input is 1, what is the output of OR operation, what is the output of AND operation? Whenever one of the input is 0, what is the output of OR operation, AND operation, and so and so. We are having the proof of all these relations, first 4 relations with the work what we had with the truth table. If you come in general, the proof of such Boolean equation. The proof of such Boolean equation is possible with the 2 procedures. One procedure is very similar to the normal conventional algebra procedure. In the normal conventional algebra, whenever we want to look to the proof of any relation, we may start with LHS expression. After some mathematical manipulations, we will try to look to the result is to be RHS. Or we may start sometimes RHS expression. After some mathematical manipulation, the result we may read LHS. Either way, starting with LHS reaching to RHS or starting with RHS reaching to LHS, if at all we are speaking that relation is true. That relation is true. The similar procedure is possible for us to use even in this Boolean algebra to see the proof of any Boolean equation. A part of this procedure, alternatively, we are having other procedure to see the proof of the Boolean equation. The other procedure is we are developing the truth table for LHS expression as well as RHS expression. After developing the truth table for LHS expression as well as the RHS expression, we will be comparing the results of LHS and RHS expressions. We are comparing the results of LHS and RHS expression. Of course, the comparison must be row-wise. The comparison must be row-wise. If the row-wise, the results are same, then we are speaking that relation is true or the property is true. Row-wise, if the results are same, then we are speaking the relation is true or the property is true. So it is the other alternative procedure to see the proof of any Boolean equation. Let us try to look the proof of this distributivity with this second procedure. The property what we are looking, the property is on 3 variables, so that we need to list all possible values on these 3 variables. If we list all possible values on 3 variables, these are the possible values on these 3 variables. If we look to the LHS result, LHS expression we are having is A or BC. If A is 1, this B and C may be of anything, 1 or with anything is 1. It is the one what we are having on the property, that is the third property. 1 or with anything is 1. So, if A is 1, B and C without bothering what the B and C value may be of anything, we are reading output is 1. So, based on this, we are looking for the last 4 rows, A is 1. Hence, LHS result for last 4 rows is 1. Similarly, if B and with C is 1, A may be of anything, the result is 1. To read B and C is to be 1, B as well as C both must be 1. We are looking for third row, B and C is 1, so the result must be 1. For last row also B and C is 1, but we already mentioned this result is 1 because of A. So no need to write once again because of B and C, because we know based on this property 1 or with 1 any number of times it is 1. So no need to write once again. And of course, at other places the result is 0. Similarly, let us read the result of RHS expression. The RHS term we are having is A or B and with A or C. If you want to read this result is to be 1, this term must be 1 and this term also must be 1. Or equivalently we can speak among these 2 terms, if at all one of the term is 0, as and when we are looking one of the term is 0 among these 2 terms, then definitely the result of this operation must be 0. The result of this expression must be 0. So based on this knowledge, if we look here, for first two rows ARB is 0. So whenever ARB is 0, the result must be 0. For next row, we are having ARB is 1, but ARC is 0. Because of ARC is 0, the result is 0. For next row, ARB is 1, ARC also 1, so it is 1, and so on. We can read like this. So later, as I said, we are comparing the results row-wise. If the row-wise results are compared, the row-wise results are same. Once row-wise results are same, the relation what we mentioned is true. The property what we mentioned, distributivity, is true. The dual of this distributivity is A and with B or C is equal to AB or with AC. It is the dual of this distributivity. As and when Y is the dual of X, as and when Y is the dual of X, while giving the proof to the X, there is no need to see separate proof for Y. There is no need to see separate proof for Y. default the proof of X is valid even for Y, or vice versa. It is one of the usage of this duality. Whenever we are having two expressions, they are dual to each other. While giving the proof to one expression, no need to see separate proof for other expression as and when it's a dual. In other way, while having one expression A, one expression say X or A, what it may be. So if you write the dual for that expression, default that result also valid. So you can develop a new expression or new equation using this property of the duality. It is one of the usage of the duality. The other usage of duality is, of course, it is more relevant to the EC students, EE students. The other usage of duality is, it is possible to convert the positive logic system to negative logic system, or vice versa, converting the negative logic system to positive logic system. By with the help of the duality, possible to convert the positive logic system to the negative logic system, or the negative logic system to positive logic system. It is one of the other usage. So what is this positive logic system? What is the negative logic system? It is more relevant terms in terms of voltages. So it is more relevant to the EC students, EE students, and instrumentation students. As computer science students, no need to bother much. But as a matter of interest, for knowledge point of view, just I am mentioning the other usages. We are having possibility with the help of the duality, positive logic system circuit can be changed to the negative logic system circuit, or vice versa. Let's go listing a few more relations. A or with A complement B, it is A or B. Similarly, A complement R with AB is A complement RB. It is possible to verify these relations with the help of the distributivity and, of course, using few other earlier properties. You can prove by using this distributivity and few other earlier properties. You can verify. You can take some time and you can verify using this property. You need to start the work with the distributivity, and later, of course, you need to use some other relations what I mentioned earlier. If you try well, the seventh one, if you look, A or with A complement B. By using distributivity, possible to read as A or with A complement and with A or B. From the fourth property, we know A or with A complement is 1. And from the second property, we know 1 and with anything. 1 and with anything. Anything is A or B here, is A or B. Hence, we are looking that is A or B. Of course, the dual for this is A and with A complement RB is equal to AB. Similarly, possible to try for 8th using distributivity. You need to start with the distributivity and, of course, few other earlier properties later. So, if we try well, this will be A complement and with A or B is equal to A complement and B. As a dual, of course, we are reading. And also we can list A or with AB is equal to A. And of course, to read this result, we are not using distributivity here. To read this result, simple work we are doing, we are having A as a common among the two terms. So within the parenthesis, it is 1 or B. While taking the A as a common, within the parenthesis, it is 1 or B. From the third property, 1 or with anything is 1. From the second property, 1 and with anything is anything. Anything is A. The dual for this is A and with A or B is equal to A. So I listed here these couple of properties, couple of relations. While noting all these, we'll be having, as a student, you will be having a question. Okay, we are learning so many things, we are noting so many things, but where effectively we are using all these is the question. As a student, definitely is a question to you. So let us try few examples. From those examples, it is possible for us to understand where it is required for us to use these relations, or what is the importance of these relations possible for us to speak.